So thanks to the organizers for the invitation. It's a pleasure to be here. So my talk's about the logarithmic Hilbert scheme, but the place I want to start at is the ordinary Hilbert scheme. So today, I'll fix X, toric, projective. The words toric and projective are just there, like, for the sake of explaining it well. They're not actually important for anything I'll say. And to study X, we can study an associated moduli space. And so in particular, I'm going to study the Hilbert scheme. So what is the Hilbert scheme of X? Well, to define a moduli space, I can give you its functor point. So I can tell you the data of a map from some test scheme to my Hilbert scheme. And what is that data? That's the data of a closed subscheme inside X times S, which is flat over F. So this is the moduli space whose points are closed subschemes of X. And Hilbert schemes are really complicated. So even if I'm interested in studying zero-dimensional subschemes of something quite simple, there's a lot of stuff we don't know about the Hilbert scheme. And so techniques to study it are valuable. And the logarithmic Hilbert scheme gives one way to study a Hilbert scheme. So here's the basic idea. Oh, wow, it's so much easier to round as well. So the basic idea is I'm going to take a map from Y to A1. And I'm going to choose this map such that, let me call it pi. I'm going to ask that the preimage of my generic point looks like X, and the preimage of 0 in A1 is reducible. And I'm going to ask that the pair Y preimage of 0 is simple normal process. But the preimage of 0 is some divisor on Y, and I'm just asking that divisor to be reasonable. So in a picture, what does this look like? Well, here's my A1. Here's 0. The preimage of 0 looks some reducible guy. And I'm going to write that as W1. So it's got, in my picture, it's got two components, W1 and W2, and they meet along some divisor, W12. Generically, the preimage looks like my original variety. Yeah. And then a common strategy in algebraic geometry is if I want to understand information about X or information about a moduli space associated to X, I'll study the moduli space of the preimage of 0, the degenerate object, and that will give me information about the generic fiber. So examples of this strategy in real motor theory, it's recently been very useful. In cumulative geometry in particular, this is how we prove a huge amount of various theorems. Okay, so the point was that I originally wanted to study the Hilbert scheme of X, and I've changed the problem. So actually it's going to be enough for me to understand the Hilbert scheme over the special fiber. But is that an easier problem? Well, here's the dream. Here's something which would make it an easier problem. So I'm just going to zoom in now on that special fiber. And I want to study the Hilbert scheme of something reducible. Now, a Hilbert scheme is a moduli space of closed subschemes. So again, that was W1, W2, and W12. If I draw a closed subscheme, it looks something like this. And what the dream would be to say that if I want to give you a closed subscheme of this whole special fiber, that's the same thing as giving you a closed subscheme of W1. So a point in Hilb of W1. So that would be this component. A point in Hilb of W2. And then they better agree on that intercept. So it would better be a fiber over Hilb of W12. And the dream would be that this would be the Hilbert scheme of the special fiber of phi inverse of 0. This would be really nice because I started with the Hilbert scheme of something maybe a bit complicated, and I've turned it into a problem about the Hilbert scheme of something which is hopefully simpler. But there's a problem with this. And the problem is that I took this fiber product over the Hilbert scheme of W12. And W12 is a divisor inside W1. So here is the problem. There is no map from, so let me fix XC, a simple normal crossing pair now. What does that mean? You should think like projected or toric variety, smooth toric variety in its toric boundary, for example, projective space and the coordinate lines. There is no map from the Hilbert scheme of X to the Hilbert scheme of D. And this is a disaster for this idea because I wanted to take the fiber product over something, but there's no map. So this dream, it can't work. But essentially then what this talks about is a fix for this problem. And that's what the logarithmic Hilbert scheme does, or one of the things it does. So to make progress, let's think about what this map should look like. So if I have, let me take the smooth divisor. And I want to think about a map from the Hilbert scheme of X to the Hilbert scheme of D. A point in the Hilbert scheme of X, so X is my circle, and then my divisor we'll have in blue. And then a point in the Hilbert scheme is this red subscheme. How do I get a point in the Hilbert scheme of D? Well, I just take my divisor and I restrict my subscheme. So this is the map I wanted to write down. Okay? And my claim is that this is not a map. So why is this not a map? Yeah, okay. So let's move forward. Where is the trace of it?
It's somewhere behind.
Oh, it's like, isn't it?
No?
Oh, maybe.
Maybe they're on the right.
Oh, it's on the screen. Ah, thanks. So we were saying that there's no map from the Hilbert scheme of X to the Hilbert scheme of D, and I'm just going to explain what the problem is. So I'm going to take this picture. And I'm going to degenerate it. Actually, maybe I'll just do a Hilbert scheme of points, a bit simpler. So I can take, to be concrete, X is P2, D is the zero set of X, and I'll take the closed subscheme to be the zero set of Y X minus T. And then I'll take the limit as T goes to 0. And what will happen is when T is non-zero, I have some point in P2 away from my divisor. When T equals 0, that point is going to come and it's going to fall into this divisor. So that's what's happening in the Hilbert scheme of X. What's happening in the Hilbert scheme of D? So this is the way T not equal to 0. This is T equals 0. In the Hilbert scheme of D, when T is non-zero, my point doesn't lie in that divisor. When t becomes 0, suddenly my points appeared out of nowhere. And this is not allowed in the Hilbert scheme. Basically, because in the definition of the Hilbert scheme, I had this word flat. And that tells me that this is not allowed. Okay. So this is the problem we have to solve. But the good news is there is an open set on which this map is well defined. So what does this open set look like?
Not fix the Hilbert polynomial something?
If you fix a Hilbert polynomial, you fix a union of connected components so that it becomes standard.
Open so you get some sort of stratifications. That's, I mean, the Hilbert polynomial is something.
Yeah, the Hilbert polynomial, it makes sense in everything I'm going to say, but it doesn't affect anything I'm going to say. Yeah. It's just if you want it to be bounded, you fix the Hilbert polynomial. So yeah, absolutely everything I said you can fix. Okay, where was I? Okay, so yeah, so the map from Hill of X to Hill D is defined on an open set. It does make sense on an open set. And I'm going to call that open set Hill block of X rel D. I've drawn that wrong. Okay. Yeah, okay. I want the Hilbert scheme of X, Hilbert scheme of D, rational map. Inside here, I have the log of X rel D, on which this map is defined. I'll tell you what this locus is in a minute. It's just some open subscheme. And there's of D. What I'll do is I will fix X sum over I GI, simple normal crossing path. So these are just the irreducible components of D, and we'll have a map defined on this open locus. Okay. And then what's the theorem? Well, the theorem is that this guy is not compact, because we saw that in one parameter families, I can take a limit and something breaks. So if I restrict to an open set where everything works, then I'm going to be in trouble. I'm not going to be compact. It's correct. Yeah, exactly that. So that, yeah, that's exactly this map. This guy lives inside the old blog of X rel D, and that has a genuine map to a blog of D I intersect J not equal to I D I intersect J. Okay. And then the theorem
On the right, on the bottom right and center right, you have different things under.
Also, it's a union, I think.
So on the right,
Sorry.
we like.
as in that should be that.
And there's also a
and
DI missing there.
Ah, thanks. Yeah. So the theorem is there is a proper space Hill blog of XLB, which fits into the following diagram. So the key point is we didn't have this map here. It did exist on an open set, but the open set wasn't proper. And so what we've done is we've constructed a moduli space which is proper. Therefore, in particular, you can do things like intersection theory. And this open set is contained inside that log. So I guess I'll just tell you what this locus is, where the map is defined. And it's simply the locus where if I take the equations of B and I pull them back, they form a regular sequence on my subscheme. So 7, 3. Transverse if that's is transverse if the equations of C are a regular sequence or form part of a regular sequence of that. I also want to add a couple of remarks on the theorem. So this was the case that the Hilbert scheme of curves was done by Devesh Malik and Drew Ranganathan. The case that D is smooth was done by Lee and Wu. And then Mattia Taupo Van Siebert and Richard Thomas have an alternative approach, which does a very similar thing to this. Other things to say. So a Hilbert scheme is a special case of a quad scheme, and everything I'm going to tell you just works exactly the same way for quad schemes. And the third thing I wanted to say is I wanted to go back to this definition of a Hilbert scheme. And I put the word, what's the question? I put the word log on the Hilbert scheme, and something that log geometers like to do, they like to take definitions in algebraic geometry, and they like to put the word log everywhere. And one way to be sure that the thing I'm going to talk about is kind of natural is to take the definition of Hilbert scheme and ask what happened if I put the word log everywhere. So if I put log versions of flat on the integral if you're a log geometer, the log version of a closed subscheme, well, a closed subscheme means kind of injection, so monomorphism, and closed means it's proper. So now if I take proper monomorphisms in the category of log schemes, then this becomes the log Hilbert scheme. So really, the point of just telling you that is to convince you that this is kind of a natural definition. But I'm going to tell you a much more kind of geometric way of doing this space now. That's fine. Okay. Cool. Are there any questions?
I think I missed this, and it's probably my fault. Hilbert log is the transverse subvariety, same definition.
So Hilbert log with the circle at the top
Yeah.
is the open subscheme of Hilbert where things are transverse.
Okay.
When you don't have the circle, it's compact. And so we've had to do something extra. So I'm about to tell you what that extra is. Okay. So as I just said, if I only care about transverse subvarieties, then I'm not going to be proper. But I really want to be proper. And if I want to check if something's proper, I should think about the evaluative criterion for properness. So the starting point to understand what the points of this are is to think about the evaluative criterion for properness and exactly why it goes wrong when you're trying to study something which is transverse.
I have a simple question. So Hilb log 0 is an open subset of both Hilb and Hilb log.
Yeah.
So should I think of Hilb log as being some kind of blow up of Hilb X?
That's not true in general. If you, in nice cases, that is true. So for example, one of the simplest examples of a Hilbert scheme would be projective space, which is hypersurfaces. And in that case, moduli log Hilb of hypersurface in the toric is exactly a blow up. Exactly a toric modification. But in general, that's not true.
But you're trying to kind of resolve. My point is you're trying to resolve a map, right?
Yeah. But I'm doing it in kind of a natural loggy way, which means there might actually be an extra component which is suddenly appeared. So let's go to the evaluative criterion for properness, and let's think about what goes wrong. So maybe the simplest example of a pair is I could take P1 and I could take 0 union infinity. So that's a simple normal crossing pair. And I want to think about the log Hilbert scheme of P1 with 0 union infinity. So if I want to check the evaluative criterion for properness, we can think about where it can go wrong. So this is my way of drawing P1. And P1 has 0 on it, and it has infinity. And a point in the Hilbert scheme would be a closed subscheme of P1. So that would be some point here. Maybe we'll just do 1 point for now. And then what I'm going to do is I'm going to send that point into 0 or infinity. So maybe I'll send it into 0. And as t goes to 0, what would happen in the ordinary Hilbert scheme is this point would run into here. So I'm thinking about the family. If this has coordinates y0, y1, it would just be y0 minus t y1. And in the ordinary Hilbert scheme, something non-transverse would happen. Let's go and fall into the boundary. So let me draw this same diagram in a more suggestive way. So what I will draw is so this is an example. Sure. So this is an example of so this is a family in Hilbert over spec the double round brackets T. That's generically what this is for T non-zero. Such that if I took the limit in the Hilbert scheme, as I sent T to 0, I got something non-transverse. So I said that this open locus wasn't compact. That means that the evaluative criterion for properness fails. So I've given you an example of where the evaluative criterion fails. Okay. Such that a limit in Hilbert not transverse. So this is what I need to fix if I want to compactify. So let me redraw the picture. And what I will redraw is I will show you the entire family. So I'm going to take maybe P1 times spec T double square brackets T. Inside there, I have in P1 times generic point. Sorry, what am I saying? 0 times spec T double square brackets T. I have infinity times spec the double square brackets t, and this comes with a map to spec the double square brackets t, where the preimage of the special point of spec c double square brackets t is this divisor here. And transversality failing, so generically on the generic fiber, I don't hit either of these divisors, but on the special fiber, I do. So this is transversality failing on the special fiber, because I've come and I've hit the zero section. I've hit my special divisor, so components fallen into there. That's not a transverse thing to happen. And so what I want to do is I want to stop this from happening. I want to stop my points from falling into this divisor. And in algebraic geometry, I now have two subschemes which are intersecting, and I don't want them to. And so there's only one thing really for me to think about doing, and that thing is blowing up. So what I will do is blow up this guy here. So if I blow up this intersection point, what's going to happen is I'm going to have an exceptional here, and my red curve is going to come and hit in the middle of the exceptional. So away from my problematic divisor now. Picture does not look like it's away from. It's going to come and hit it away from the exceptional divisor. But the thing is that now, after doing this blow up, the preimage of 0 doesn't look like P1 anymore. It looks like two P1s chained together. And so this is how we can give kind of a first definition of, or a first kind of actual geometric definition of what log Hilb is. So let me define an expansion of x is what happens when you do the following. So first, take x times a1 and do a toric modification. And then take the preimage of 0 in a1. Okay, that's what an expansion is. So x was a toric variety. And so I have x times a1. Yeah. So I started with x as toric variety. In general, it's called a log plot, but today we can just focus on the toric case. So for example, if I took p1 times a1, I could do a blow up, and I would get these two p1s glued together. And then definition, or well, it's not quite a definition, but the points of log Hilb. So log Hilb is the moduli space of closed subschemes of expansion. So what I'm telling you is that this is all I need to do. So I want to check it's proper. I want to check the valuative criterion for properness. What I'm always going to do is I'm going to take some family over spec over DDR, or let's go stick with A1 for a second. And transversality is going to fail on the special fiber. And I'm saying that if you let yourself do toric modifications, then you can always make the special fiber transverse. But the price you paid for that is you're no longer studying subschemes of X. You're studying subschemes of expansions of X. Okay? And so now I'm gonna talk about how this links to tropical geometry.
And so this is all modular some equivalence relation.
Yeah, yes, exactly, yeah. There's an equivalence relation that, yeah, I'm gonna go around. If you ask me at the end, I can tell you what it is precisely because I will have got to that bit. Okay. So, now there's a dictionary. Between subdivisions of fans of x times a1. That's the same thing as a current modification. Okay, so let's do the P1 example. The fan of P1 times A1 looks like this. And then I do some turret modification. I do that. But then what I can do is I can take the slice at height 1. And this gives me the third part of my dictionary, which is polyhedral subdivisions of the fan of x. So what I'm doing is I'm taking my subdivision in yellow, I'm just restricting it to that red line. And what I'm getting is I'm getting a red line, which is the same as the fan of P1, with some yellow dots on it, which is just recording exactly which toric blow up I have to do. Okay? And this is where things start to look tropical. So here's one example of a picture I'm going to use to record an expansion. But if I took x to be P2, then the fan of P2 would look like this. And on it, I would have some higher dimensional tropical gadget like that. So these expansions are going to be, sorry, should be complex. They're going to be tracked by this kind of picture. Okay. So we've seen that to get the valuative criterion for properness, what we need to do is to do some toric flow. But now what we want to do is we want to understand which toric blow up I have to do. And I want to understand that in a tropical way. So that's what I'm going to do next. So what I will do
clarifying here, I'll just put both together. So you have this closed subscheme intersecting a divisor, and then changing a family. And
so I have a closed subscheme which doesn't have any components living in the divisor, generically. And I want to compactify the moduli space of these. And what can go wrong is something can go and fall into a divisor. And so what I should do to fix that is do some blow up of the total family. So that my subscheme no longer falls into that divisor. And then the moduli space of these, after you do some work, is what the logarithm of the scheme is. And it turns out.
What you're saying, you're saying, don't quite know how to blow up.
Yeah, I want to control what blow ups I do. So yeah, I want to control what blow ups I do. So here's the basic question. So I have Z, a subscheme of X times A1, where X is toric, for which toric block of X times A1 is Z transverse. So in this case, it was kind of simple because it was just P1 meeting, it was just two lines, it was two-dimensional case. But in general, controlling these, we need to be a bit more careful. So I can change the question to make it a tiny bit more general. And I'll just say for Z in any toric variety, how much do I have to blow up so that Z becomes transverse? And then the theorem, and this is joint work with my supervisor, Drew Ranganathan. And I'll remark in a second all the other people whose work goes into it. So for which toric blow-ups in my Z transverse, well, okay, let me explain it before I do. Sorry. Okay, so Z lies inside a toric variety. So I'm going to suppose that Z has some ideal I. Now, here's a fact, which is familiar to people who thought about Grosvenor theory, but if not, that's okay. For each point W in the co-character lattice of the dense torus of X, there is an ideal in W of I, which lies in the coordinate ring of X naught. So that's just some fact. If you know Grosvenor theory, this is just taking the initial ideal and putting it in the coordinate ring of the torus. And then the Grosvenor stratification of the fan of X is the locally closed stratification of this fan where W is constant. Right, sorry, in W I is constant. So I'll do an example. Was there a question?
Could you remind what is MX?
The co-character lattice, like, so the fan lives in something, which is the co-character lattice tensor key. So that's it's just where it lives. Okay. Cool. So then the theorem. Okay, no, so I want an example. Yeah, the theorem. So the example is the maybe I'll work in A3. So I want to convince you that this Grosvenor stratification is really a tropical gadget. So in A3, take the 0 set. So I'm going to have coordinates X, Y, Z on here. I'm going to have the 0 set of X union X, the 0 set of X minus 1, Y minus Z. This is like a line and a plane in a, sorry, X2. a line in a plane in A3, and then I can draw the fan of A3. And what this stratification will do, it will take the face of the fan corresponding to the okay. Yeah, I wrote this down. I will look at my notes so I don't lie to you. My notes are wrong. That's great. Okay. So I'm taking a line and a hyperplane, and what I'm seeing on the level of fans is I'm seeing a tropical line and a tropical hyperplane. You should maybe ignore that example because I managed to mess it up. But you should not ignore the following remark. If I have Z inside a toric variety, there's a well-known thing called the tropicalisation of Z. And that is a subset of the fan closely related to the Grosvenor stratification. Because the Grosvenor stratification remembers where, like, what in WI is everywhere. The tropicalisation just remembers whether it's one or not. This is a slight refinement of tropicalisation. It's able to see lower dimensional things hiding behind higher dimensional things. Okay. So we have, and then the theorem. Remember, we wanted a tropical criterion for transversality. What this tropical criterion will say is that this Grosvenor stratification tells you everything you need to know about whether you're transverse. So the theorem, if I take Y a toric variety, Z in Y, the closed subscheme, with no components in the boundary. In the toric boundary. Then Z is transverse, even only if each stratum in the Grosvenor stratification is a union of cones in the fan effect. Okay. Sorry. Why? Why? Yeah. Sorry. I thought you were asking why the theorem. Okay. So that's the thing which that would control exactly which monomial blowups I should do. Okay, so what have we got so far? So we wanted to we started by trying to study transverse subschemes in the toric variety, and they weren't compact. And what we really realized we needed to do to make the valuative criterion of tropical work is to do some toric blowups. And now we have kind of a tropical criterion for exactly which toric blowups work. And this tropical criterion motivates the following definition, which is good for our purposes, and a slight variation on the thing in the literature. So definition, a piecewise linear space is a cone complex. So let me just say fan, in case people are scared of cone complexes, with a locally closed stratification such that there exists a subdivision of fans such that each stratum is a union of cones. So let me do an example immediately. So I want to think about the fan of A3. You can read. So I'm about to give you an example of something which is a PL space, and then I'll give you something example of something which isn't. So what I could do is I could take the fan of A3 and I'll draw like a cone over picture, so height 1 slice. And then I could just stick a ray in the middle of it. So what I've done is what I'd not be allowed to do is I couldn't take the fan of A3 and subdivide it as a fan by sticking a ray in the middle. Because when I stuck that ray in the middle, this region here would not be convex. And cones in a fan have to be convex. But piecewise linear spaces remove the convexity. So I'm allowed to stick an array in the middle of a 3-dimensional space. And that's the difference between a piecewise linear space and a cone. So that's an example of a piecewise linear space. What would not be an example? So for example, if I took the fan of A2, I couldn't just stick in any old curvy locally closed stratification because it has to admit a refinement by a fan. So really, this a union of interiors of cones for some subdivision. That's an equivalent way of saying it. Possibly a better way of saying it. So that kind of thing would not be allowed. Okay.
In the first example, like thinking of R3, this is just like the diagonal.
Thinking of exactly the diagonal. It's like the line 1, 1, 1. So I wouldn't be allowed to stick a ray in the middle of a 3-dimensional space without subdividing it. So that's a piecewise linear space, and I can refine the stratification to get a cone complex because I could just add in some extra kind of scaffolding, and then I get an honest cone complex. Okay. And this is so really, if you're familiar with the definition of fan, in the definition of fan, cones have to be convex. This does not have to be convex, and that's the whole point of it. Okay. And then I go back to my favorite board, because we've defined the tropical gadget, and this is a talk about Hilbert schemes. So now what I want to do, so before I was talking about moduli spaces in log geometry, and I want to talk about a more tropical moduli space. And so instead of defining a functor on the category of schemes, I'll define a functor on the category of fans, or on rational polyhedral cones if you're an expert. So I'll tell you what the data of a map from a rational polyhedral cone so this is, you can think of it a bit like a tropical version of a Hilbert scheme, but it's called SUP. And it's SUP of some cone complex or some fan sigma. And the data of a map from, maybe we'll call that tau, to SUP of sigma is very much like the definition of a Hilbert scheme, except that now I'm going to take sigma times tau, mapping down to tau. And instead of taking a closed subset scheme, I'm just going to take a piecewise linear space, which is a subdivision. So refines it's just this cone complex with any stratification you like. And then I better say some flatness words, which I'm not gonna get into. Okay, so we started with an ordinary Hilbert scheme. We defined a log Hilbert scheme. We've defined the stack of tropical supports, which the first time you hear about it, you should think of as kind of like a tropical version of a Hilbert scheme. And now I'm going to tell you about the connection between the log Hilbert scheme and this tropical gadget, and why this tropical gadget is essentially the only way we know how to access log Hilbert scheme. But maybe before I do that, I'll give you some examples of what this guy looks like. So, for example, something that people are often interested in is the Hilbert scheme of points on A2, say. So, if I was doing the tropical version, if I wanted to understand the of the fan of A2, what would that look like? Well, a point of this would be the data of a locally closed. So if I want a map from the simplest code in the world, which is non-trivial, is R positive, so it would be a piecewise linear space subdividing the fan of A2. So I'm going to draw the fan of A2 at height 1 and take a cone over picture. And what that looks like is it looks like the fan of A2 with some dots floating around. Okay. Cool. So I have like 10 minutes. And then, so the first thing to maybe say about this tropical Hilbert scheme is it's kind of reasonable. So I guess I've defined for you a bunker of points, and I want some niceness property. The best niceness property I could hope for is that it would in fact be a fan or in fact be a cone complex. But that turns out not to be true. But what is true is that the of sigma is a piecewise linear space. So there's piecewise linear spaces. It makes sense to talk about a map from a cone to them, and so they also define kind of sheaves on the category of cones, and so is well behaved in this sense. But a much more important theorem for what we're interested in today, I guess. Oh, sorry. When I told you about transversality, I forgot people's names. The theorem about transversality, I should say, Kevelev showed that there exists a toric modification, and then Martin in the Kotkin case is in his thesis the statement. The statement is in like the introduction there. Yeah. Okay, so here's the fact, and we can thank Cavalieri, Dan, Martin, and Jonathan Wise for this. Whenever you have a tropical gadget, a dictionary from sheaves on category of cones in particular, surf is a sheaf on the category of cones to algebraic geometry gadgets. And this functor, they call A star. I'll call A star. Okay. So why did I tell you this fact? Why this is interesting is it's saying to us that if I define an object in tropical geometry, there's an associated algebraic geometry gadget, and all the information about the algebraic geometry gadget is entirely captured by the tropical geometry of what's going on. So this is really a combinatorial gadget, something I can really get my hands on and understand. And this is really useful for studying the log Hilbert scheme. for the following reason. And the reason is that there is a map from the log Hilbert scheme to this combinatorial gadget. So, and this, the reason that this theorem I want to emphasize is the only way I know how to prove things about the log Hilbert scheme. So this, the point is that there is a map from the log Hilbert scheme of X or LD to a combinatorial gadget A star sup of the fan of X. Okay, so there is a map with algebraic fibers. And this map captures everything you, like this captures all the extra complexity that comes from this being a log Hilbert scheme and not an ordinary Hilbert scheme. In particular, so maybe if I call this map alpha, the preimage of any point is a relative Hilbert scheme. Sorry, just an open subset of the Hilbert scheme. In fact, if you get like an open cover of the log Hilbert scheme by taking like a cover of this guy and taking relative Hilbert scheme. So really, this map is the only way I know how to access information about the log Hilbert scheme. Okay, I have 3 minutes. I could do an example, but I think maybe I'll stop.